Hi, I'm Alex Hugh, and I'll be going over my presentation for algorithmic primitives. So I'll be going over the stable roommates problem. So the problem statement is that we're given an even number of candidates n, who must be paired into n over 2 matches based on their preferences. So each candidate has a strict preference list ranking all other candidates, and we must form stable pairs. Matching is considered stable if there are no two candidates who would both prefer to be paired with each other over their current matches. So this might sound similar to the stable marriage problem, but it differs slightly, and this leads to a very different solution. So the stable roommates problem differs in that it involves pairing within a single group of candidates as opposed to two distinct groups. So each individual only ranks or must rank every other individual in the stable roommates problem, while each individual only has to rank those in the other group for a stable marriage. So this figure on the left is a representation of the stable roommates problem, while the figure on the right is the stable marriage problem. So the stable marriage problem is more of a bipartite matching, while stable roommates, as you can see, you're matching within one group or set. So let's walk through a problem and go through the algorithm that would solve this problem. So find a stable matching if it exists for the following preference table. To read this table, this is the preference list for Alex in the first row, and from most to least, and then for each of the other people. So to start off, Alex would make a proposal to Bob. Since this is the first proposal, we just leave this as the current proposal. Now Bob proposes to Elise. Since Elise has no other proposals, this will stand. Now Carol proposes to Bob. Now, since Bob already has a proposal from Alex, we have to determine which one to keep. And we go to Bob's preference list. We see that Carol is ahead of Alex on his preference list. So then we remove Alex's proposal. So we remove Bob from Alex's list, and now Alex doesn't have a proposal, or Alex hasn't made a proposal. So now we must make Alex propose to the next highest person on his list. So to Daniel. And since Daniel has no proposal, this proposal will stand. And now we go to Daniel. So Daniel will propose to Carol. And since Carol has no other proposal, this proposal will stand. Now Elise proposes to Bob. But since Bob already has a proposal from Carol previously, we must determine once again which one to keep. So we go to Bob's preference list. We see that Elise is ahead of Carol, so we must remove Carol's proposal to Bob. So we remove Bob, and now we must make a proposal from Carol again, since she's not proposing to anyone anymore. So Carol proposes to Francis, and Francis has no proposals, so this proposal will hold. And now Francis proposes to Alex, and since Alex has no proposals, this proposal will hold. So now we must check whether which things to remove. So basically, since Alex is making a proposal to Daniel, we can remove all of the people on Daniel's preference list that are ranked below Alex. So we can remove all three of these, so Francis, Bob, and Elise. And then we can also remove them from the corresponding other lists. So since Francis, Bob, and Elise were removed, we removed Daniel from Francis, Bob, and Elise's list. So now we go to Bob, and we do the same thing. Since Bob proposed to Elise, we remove Alex, Francis, and Carol from Elise's preference list, since they're all ranked below Bob. And since we removed Alex, Francis, and Carol, we must remove Elise from those preference lists as well. So that's why we're removing Elise from all three of these lists. And then we do the same thing for Carol. So we remove Bob since it's below Carol and Francis's list. And then we remove Francis from Bob's list. For Daniel, there's no one ranked below Daniel on Carol's list, so we move on. Same for Elise, no one below Elise on Bob's list, so we move on. And then Francis, we see that Francis proposed to Alex, so we look at Alex's preference list. Since Carol is below Francis, we remove Carol, and then we remove Alex from Carol's list. And now we're left with the following table. I just shifted everything to be more organized. So once we reach this stage of the algorithm, if no list of preferences is empty, we have a stable matching, or currently we have a stable table. So there's a potential to find a stable matching. So if any list has more than one person, we must check for cycles. So we can see that Alex, Carol, Daniel, and Francis all have more than one person on their list. So we proceed to the cycle checking step. So if there exists a cycle, we must remove it. And to explain what a cycle is, an example would be if A prefers B over their current roommate, B prefers C over their current roommate, and C prefers A over their current roommate. So for cycle removal, there's a simple algorithm as a part of this whole algorithm that we can use to remove cycles. So let's define P0 as Alex, since that's the first entry. So we'll just define P0 to be Alex. Or it has to be the first entry with multiple people in it. So we'll define it as Alex. The second person, we'll define Q sub 1 or Q sub I as a second person in PI's list, and P sub I plus 1 as a last person in Q sub I's list. So going by this, we can make the following table right here. So P0 is Alex, and then we go to Q0, which is the second person in Alex's list. So that's Francis. So we put Francis in Q0, and now we've moved to P sub 1, the last person in Q sub 0's list. So the last person in Francis's list is Carol. So we put Carol as P1. And then similarly, we go to Carol's list. We see that Daniel is the second person, so we put Daniel here. And then finally, we go to Daniel's list and we see Alex is the last person. So we put Alex here. And once we have the same person appear twice in column P, then we can determine that there indeed exists a cycle and we must deal with the cycle. So since Alex appeared twice, there is indeed a cycle. So what we can do is remove the proposal from Francis to Carol and from Daniel to Alex. So from Q sub I to P sub I plus 1. So we remove all such proposals. So I've highlighted these proposals here. So Daniel to Alex would be this one. And then Francis to Carol would be this one. And then we also have to remove the corresponding people from the one being proposed list. So that's why there are 4 being removed. And after this step, we're left with the following stable matching by removing each of these 4. And then the matching would be Alex to Francis, Bob to Elise, and Carol to Daniel. So now to go over the time complexity of this algorithm, in the worst case, each participant will propose to all others before finding a match. So the total number of proposals, or not the total, each participant will be making n-1 proposals for each of the n participants. So there will be n times n-1 total proposals. So this step will take O of n squared time, and it is the limiting factor in the algorithm. So the entire algorithm will be O of n squared, where n is the number of participants. So now I'll be going over a proof of correctness. This is a very basic proof, since the full proof will be very difficult to explain. But essentially, this proof will be broken down into three parts. That the algorithm will indeed terminate after a finite number of proposals. If a stable matching exists, the algorithm will find it, and the matching produced by the algorithm will be stable. So, for algorithm terminating, since the number of participants is finite and each participant has a finite number of proposals, the algorithm will eventually terminate when no unmatched participant can propose to anyone else. So for why a stable matching exists, the algorithm will indeed find it. This is because the algorithm maintains a list of proposals and matches. So once a match is made, it can't be broken unless there's a preferable alternative for one of the participants. And each participant only proposes to those that they prefer and accepts the best option available to them at any given time. So because of these statements, the algorithm will systematically eliminate these unstable pairs. So only stable pairs will be remaining once it finds a matching. And then finally, why the matching produced by the algorithm is stable. The matching is stable if there are no two participants who prefer each other over their current matches, this is just the definition of stable. So given that the algorithm allows participants to propose based on their preferences, any unmatched pair must involve at least one participant who prefers their current match over an unmatched participant. So by construction, no pair of participants will exist who prefer to be matched with each other over their current matches. So to give a conclusion, this is the general explanation of Irving's algorithm. Irving is the person who came up with this algorithm, which is used to solve the stable roommates problem. And it runs in O of n squared time, as previously mentioned, and is guaranteed to find a stable matching if one exists. Although there could be multiple stable matchings aren't necessarily unique, but this algorithm will find one such matching if it exists. And yeah, that's basically my presentation on algorithmic primitives in the stable roommates problem. So thank you.